Um, one of the hopes behind variational quantum algorithms is that it might be more robust to noise. Example, systematic over rotation, under rotations. I think that's still a little bit speculative, but it's primarily a NISQ framework for running quantum algorithms. NISQ meaning near-term quantum machine. Okay, and importantly, in standard variational quantum algorithms, the quantum circuit is fixed in structure, and what the classical computer does is it optimizes the variational parameters, right? So it's a big optimization machine. That's the primary demand that you make on the classical computer. And what I will talk about today are more like what we call adaptive quantum algorithms, which put different demands on the classical computing side. So what I'm trying to do is take away some of the demands on the classical computing side, because we know that the large-scale optimizations you need to do when you have many parameters are very difficult to do. There's lots of local minima. Your estimate of the cost function is noisy, and so there are lots of failures that we've seen where that just getting to the classical optimization step working is difficult at scale. And so what I wanted to think about is a different approach where this is what I would call the standard approach, where you just run your circuit, you measure something, and then that sets how you vary the parameters in the next run of the circuit. Okay, it's a standard variational paradigm. Adaptive would be this: so you run, one layer of your circuit, you measure something, and that tells you how to tack on the next layer of your circuit. So you slowly grow your circuit using measurements at the output of your previous circuit. Okay? And so, importantly, control theory can be a really useful framework for thinking about quantum algorithms in this context, in the adaptive context. And intuitively, this is because you're basically driving a many-body system in the direction you want it to go, right? It's a very control kind of inspired problem. And the two variations that I'll show you are we get at the solutions basically using control theory. Right, and this is maybe specifically a point I added for this audience, where you think a lot about how to integrate quantum computers with HPC, is that the demands you make on the classical computer when these adaptive algorithms can be very different from conventional variational algorithms, where it's just optimization. And I'll go through what those are. So I should say, I will present two examples of such adaptive algorithms. One we call Falcon, which is Lyapunov controls inspired. We've already published on that. There's a couple of papers in 2022. The other is what we call predictive quantum variational algorithms, and it's model predictive control inspired. This is still work in progress. I'll show you some preliminary results there. I should say that these aren't the only forays into adaptive quantum algorithms. There's been a slew of work, specifically some nice work from the Sophia Economou and Advances group on what's called adapt PQE. We have a slightly different take on what it means to adapt quantum algorithms, but I can get into the comparison if people are interested at the end. Okay, let me first jump into the Falcon work. So this is joint work with Alicia McGann, Kenny Rudinger, and Matthew Grace, all from Sandia. And those are the references for the papers. So we framed this algorithm specifically in the context of optimization, the application of optimization. But you could think about this as a way to prepare ground states as well. This is not limited to just optimization. And so in optimization, we know that many discrete optimization problems can be formulated in terms of Ising Hamiltonian. And these Ising Hamiltonians typically look like this, where you have two body Z, Pauli Z operators with some weight. And that's called a problem Hamiltonian. And you can think of this as encoding some constraint between your discrete variables in your problem. And so you have some constraint graph, and this Hamiltonian encodes a constraint graph. And the ground state of this Hamiltonian encodes the solution to the problem that you have. So if you can get to the ground state, you can just read it out and get the solution to the problem. And there's kind of two primary quantum approaches to solving these discrete optimization problems, which are phrased in terms of Hamiltonians. One is adiabatic quantum annealing, and the other is quantum approximate optimization algorithm, or QAOA. Can I just ask how many people are familiar with QAOA? Just so I know how much time to spend on this slide. Okay, about 3/4 of the range. I'll go over it quickly. So QAOA, basically what it does is it takes the problem Hamiltonian, and that problem Hamiltonian generates a unitary by just exponentiation, right? So e to the minus I, some parameter gamma, HP is the problem unitary now. You also define something called a driver Hamiltonian, which is in some sense orthogonal to the problem Hamiltonian. In this case, it's built up of just sum of local Pauli x's. And that defines a driver unitary by exponentiation as well. And QAOA, it just defines this alternating sequence of problem and driver Hamiltonian. You just apply each of those unitaries in alternating sequence. But notice that they all have a free parameter, right? So there's a free parameter associated with each one of the unitaries. And in what QAOA you try to do is you optimize those parameters in order to drive the state towards the ground state of the problem Hamiltonian. And so this is the standard kind of variational setup that I mentioned, right? Your circuit has a bunch of parameters. You optimize those parameters to drive towards the ground state, to minimize this expectation value of the problem Hamiltonian as a function of these parameters. And a bottleneck in this approach is searching for the optimal parameters. Once you get to hundreds of parameters, hundreds of layers, searching for these optimal parameters becomes very, very difficult. Okay. We can take a control theory kind of perspective on this problem and look at it as a continuous time system. And I'll map back to this discrete time circuit picture in a second. But you can just think about this as actually a continuous time evolution according to the Schrodinger equation, where the Hamiltonian is the sum of the problem Hamiltonian and the driver Hamiltonian. And I'm just going to attach a parameter to the driver Hamiltonian that can be time dependent. Okay. So preparing the ground state of HP now is equivalent to minimizing the energy as a function of time, which is the expectation value of just the problem Hamiltonian. And you can look at how that changes. You can look at the derivative of the energy in this continuous time system, right? It's a very simple calculation. You can actually define it as a Lyapunov function and demand that it decreases in time. So the notion of Lyapunov control is that if you can find a Lyapunov function that decreases monotonically in time, it will converge to the minimum. And you can just take the derivative of the energy. So the energy is, again, expectation value of the problem Hamiltonian. If you can figure out what that time derivative is, because it's just Schrodinger evolution, it's a commutator with the Hamiltonian. HP commutes with itself, so it becomes a commutator with HD and HP. And I'm going to define that expectation of this commutator as A of t. That's a scalar AT. That's this here. There's an I in there as well, so it's real. Now, if I set my control parameter beta to be negative of A of t, then this is going to be minus A squared, right, at any time. And that's a negative number, guaranteed to be a negative number, and therefore the energy is guaranteed to be decreasing. Basically a feedback law that tells you if you can measure A of t, then you can set your control parameter at any time so that your energy is monotonically decreasing. Okay. So that defines now we can go back to the circuit picture and basically discretize this continuous time evolution. And you do it through basically a trotterization that says, I'm going to take small steps in HD and HP and just repeat, just like in QAOA. But now I just have a parameter attached to the HD part, right? The HP part is parameter free. It's just evolution for some time delta t by HP. And so it looks like kind of iterations of this. There's a unitary by the problem Hamiltonian. There's a unitary by the driver Hamiltonian with a parameter b beta. I say beta n because this is the beta of the nth iteration. So how do I set the beta? I basically measure this operator A after an iteration, and then I set beta to be minus of this A value. Okay, so here's kind of a schematic of what you do. So initially you set beta to be 0. You run one layer of this thing. You run UP, you run UD with beta equals to 0. Then you measure this observable A. And then for the next iteration, you set beta 2 to be minus of A1. And then this iterates over time. And the idea is that each iteration you append to the circuit, it'll monotonically decrease the energy over time. So the energy is guaranteed to decrease with circuit depth. I should say, I like questions in the middle. So if you have any questions, please interrupt. Yeah.
What is the cost in terms of number of samples you need for each estimation?
Yeah. So I don't have maybe I have a backup slide on that. Can I get to that at the end? So we have a comparison in terms of number of shots you need for QAOA versus this, where here you're doing sequential.
But I have a question.
Yeah.
Why do you think this is gonna be an optimum way? Because at the end, every iteration, you need to make a measurement, and in quantum, this is really like the number of measurements then is gonna be huge. Because like to reach till the minimum here, you might really go a lot of steps.
Mhm.
So why do you think adapt here method it's that you are using is really efficient?
Yeah, so there's no free lunch, right? So you're removing the optimization part, but you're adding the burden that you have to do all these measurements. That's true. And so this is not something you'd want to do if your measurements are very expensive, for example. If you're, if they're way more expensive than gates, or you can't afford to do a lot of measurements. But there's ways to I should say this A2, right? It's an entirely two-body operator, at least in this. It's a sum of two-body operators. So it's not like a tomographic measurement that you need to do.
And may I have another question here?
Yeah.
So the difference here between this method and the adaptive method is that you are not doing any gradient here for the full operators, right? That you need to add for the next step. Instead, you are using this minus A1.
Right. Yeah. So with adaptive QE, you typically have a family of terms that you can add in this next step, and then you compute the gradient with respect to each of those members in the family, and then you take the steepest. Yeah.
As a little follow-up to that, when you make all these measurements, you're losing quantum coherence at every step. Is that something to be concerned about? That you're not kind of utilizing
I should say this is re-prepare, right? So you would make a measurement and then you go back and re-prepare the system again.
Okay.
So it's not a real-time feedback.
Okay.
So we're working on extensions of this for actually real-time control, control-driven algorithms.
I see.
That's a whole nother topic.
Thank you.
I think there's a question at the back. Yeah.
Could you just comment on that a little bit more, though, on the real-time control? Like,
Can I leave it till the end so that I want to make sure I cover the stuff that I have first, and then I'll. Yeah.
I just wanted to comment on like the number of things that you need to measure. If your Hamiltonian is, for example, local, and then the control Hamiltonian is also local, I think their commutator will also just lead to some local things. So you always have ON measurements, not like so even in VQ, you need to measure. You gotta calculate the gradient and plug things in again. So that measurement's always there.
Right.
It seems like in terms of that, you don't have much of a neither too much of a gain in terms of measurement or loss compared to VQ kind of things. So
so the number of number of operators you need to measure is very similar to VQE. But the thing is that you don't just measure it at the end, right? You need to measure it at these intermediate stages too. So if the number of layers you need is huge, then you need to do a lot more measurement. So there's a trade-off there. Is there another question? Yeah.
I was wondering, do you require delta T to be small to faithfully
Yes.
get the approximation?
Yeah, that's right. So this, remember the rule is inspired by this differential argument, right? And so when you discretize that into delta T, it has to be small. And that's actually one of the issues that you'll see. I'll present. And then the second part is about how to overcome that. Okay. Yeah.
Have you characterized the cost of these SPAM functions, like basically state preparation and measurement, since you are doing it repetitively multiple times?
So it depends on what you mean by characterize. So in the paper, we've, for example, run it on a device with real spam error. The other thing is that you can look at, so one of the nice things about this feedback law is that you see that you only really need to get the sign right. You need to set beta to be minus of A at T. You don't really care if it's minus, as long as you get the sign of A right, you can have some slop in that estimate. So that's actually somewhere where you gain in terms of number of shots that you need to do. As long as you're confident about the sign of your observable, you can immediately just go ahead. You don't really care about getting the magnitude right.
But the state preparation might take some time since you're doing this.
Oh, in terms of time cost, you mean?
Yeah, time cost. You're doing this to speed it up compared to classic, right?
Not necessarily speed. Speed it up compared to like what's the advantage compared to classical?
Yeah, exactly.
Okay, that's a more complicated question because we don't even know that there's a advantage to doing optimization in this way to best classical heuristics. This gives you an approximate solution, but we have very good approximate discrete optimization solvers. And so there's no established advantage between a quantum algorithm like this and classical discrete optimization solver.
And the question, why are we doing it quantum?
It's a good question. Yeah, I mean, it's a heuristic which seems to work well. I mean, so I guess okay. So there's no rigorous advantage.
We should not forget that we're doing this as a machine, do something that classical cannot do.
Sure. Yeah,
That's a bigger.
So give me an example of a problem where we do have that advantage.
Because this repetition of classical quantum, classical quantum,
Yes.
is gonna cost you a lot in terms of.
So let me ask you, what's an example of a problem that where you do have that advantage? Right, the whole field is in that position, right?
You know,
Not even factoring, right? We don't know that the best classical algorithm for factoring is not polynomial close.
okay, let me just give you another thing. For data intensive applications, this is gonna be a huge problem. But for compute intensive applications, quantum could have really a big edge over classical. That's my big.
Yeah. That's right. I mean, loading, I mean, it depends what you mean by data. If you mean classical data, yeah, I agree. We don't have a good way to load classical data. This is not a lot of data. The data that you care about is the Hamiltonian, which is efficiently specified.
You need to prepare the state.
The state is the zero state at the beginning. Oh, it's a plus state. It's a product state at the beginning. The initial state.
Maybe I missed something. Let's take this offline.
Okay. Okay, so let me give you an example. So that's Falcon. I'm going to show you an example where the problem is what's called the max cut problem, where it's a graph problem where you have a bunch of nodes and each edge is weighted, and you're trying to divide this graph into two sets of nodes, where the cut, this is called the cut, where you've divided into two. You break the highest weight when you do this cut, right? So when you add up the weights that go across this cut, that's the largest value that you could have. So the max cut problem. Like I said, this is an approximate optimization algorithm, right? So you always get the thing you're interested in is what's called an approximation ratio. So what's the value of the cost function you get relative to the minimum possible value you could get? I said it's max cut, so you should define the minus of it, and you can define it as a minimization problem. And then I'm going to show you also another metric that we plot, which is the probability of measuring the minimizing bit stream, right? So you can measure the cost function, but you also want to know what the solution that attains that value is. And so there's a probability of measuring that, because in the end of these algorithms, you typically are in a superposition of bit string. There's a finite probability of measuring the one that that is the actual solution. Okay, so here is an example. I think this was on 3 regular unweighted graphs. This is the number of qubits. The color is the number of qubits. This is over many samples of graphs of that numbers. That's why there's error bars on these lines. And basically, I'm showing you as a function of layer, as a function of number of layers of UP and UD that you do, this is now the approximation ratio and the probability of success. So the dotted lines, yeah, okay. So the dotted lines are the approximation ratio. The solid lines are the probability that you get the solution bit string. So you see that it does monotonically increase in the sense that the energy decreases and therefore the approximation ratio increases, but it gets slower and slower as you get more and more qubits. Right? You can kind of look at the number of layers you need to meet the Gurmans-Williamson bound. So I mentioned that we have very good classical approximate optimization algorithms. The best one is Gurmans-Williamson for this kind of problem. And the bound, the worst case bound that it gives you is this value. I think it's 0.9 something, 0.93, something like that. And this is the number of layers you need to reach that as a function of qubit. Right? So it looks like it's scaling roughly linearly here, but I wouldn't want to draw that conclusion given it's only up to 20 qubits. Yeah.
Are you equating layers with execution time? Or would you?
There's a constant factor difference there. So each layer takes a constant execution time. Because you need the UP layers have a lot of 2-qubit gates, they have ZZ gates. It depends if you can parallelize them. You know, that constant factor will be dependent on the hardware.
The plot on the right, like, I mean, those two lines, are they corresponding to probability equals quarter or like the Gomez-Williamson bound?
This is the Gomez-Williamson bound, the dotted line, and the solid line is the probability of a quarter of success. So typically, for the approximation ratio, you want it to get to here. For the probability of success, you could live with probability of a quarter because you just repeat the experiment 4 times and on average get the right solution.
I was asking like for the like the
Oh, this.
the small plot.
That's a good point. Yeah, these are phi is to get to a probability of quarter, and the brown curve is to get to the Gomez-Williamson.
I was expecting something like a probability of 1/4 to be almost linear-ish, but like as you go up, maybe it will go exponential because.
So it is only 20 qubits. So I mean, I'm not confident that this doesn't go exponential. Yeah.
It's good enough.
Okay. So that's the end of the Falcon part. So basically, this is a new variational inspired algorithm. We've shown an application to combinatorial optimization, but there's a follow-up paper by Alicia and team on ground state preparation. So you can also use this for ground state preparation for chemistry problems. Importantly, it's adaptive, right? Feedback from qubit measurements is used to set the circuit at future times. No optimization of variational parameters is required, so you can completely take out the burden on the classical computer. The job of the classical computer is very easy. It basically just sets beta equal to minus A, the quantity you measure, right? So maybe that's kind of boring for the HPC crowd. So, but the next part I promise won't be boring. Okay, so this is now work that we're currently doing. We call it predictive variational quantum algorithms. This is again with Alicia, also with Dominic Messina and Helen Durant from Wayne State University. Oh, sorry, these references should not be there. This is work in progress. We haven't published anything on this yet. This is a holdover from the previous slide, sorry. And even the name is tentative at this stage, so this might change. Okay, so you might have noticed that in the Falcon plot that I showed you, it takes a long time to converge, right? The circuit complexity is large. In order to get reasonable estimates of the energy, 400 layers, 500 layers. And if you go to a hardware person and say you want to run 400 layers, they will probably kick you out of the room. So that was one of the concerns we had with this algorithm. It's nice, it has some nice properties, but it does take a long time to convert. Can we do better? And so the first step in understanding whether we can do better is to understand that Falcon is intrinsically a greedy strategy, right? You look locally at the cost function, and then you decide on the next direction to move in. And you do that over and over again. So it's a very kind of greedy strategy that only looks locally at the direction to move in. A less greedy approach is you can use model predictive control for optimization. So what is model predictive control? This is kind of a control theory diagram of model predictive control. You have a system that's producing some outputs. If you've ignored this part, then basically this is open loop control, where you just say, I'm going to optimize my drive for the system in order to optimize something about the output. Right? But in model predictive control, what you do is it's a feedback system where you measure something about the system, you plug that into a model you have for the system. The model doesn't have to be exactly matching the system, but it's some model of the system. Then you use that for your optimization loop, and that defines your input signal to your system. Okay, you have the actual system you're doing experiments with, but you also have a model that you can use to predict properties of the system. And the model of the system is seeded with measurements from the system. Okay? And the model makes predictions, importantly, for a finite time horizon. The model isn't responsible for predicting arbitrary long times for the system, because that would be very difficult to do unless you had an exact model. And the control actions at the current step are dictated by these finite time horizon predictions. Okay? And so in the quantum setting, this is what we are proposing to do, which is that, so again, we're going to adapt our circuit. We're going to add new layers to our circuit. But the what you add in the next layer will depend on some prediction of the evolution of the system based on measurements you do at the previous layer. And this is kind of grayscale boxes because it's based on the model, not on the actual device. So at each time you measure something, you use those measurements to seed the model and predict forward in time. And then based on those predictions, you set what the next layer is going to be. So you might say, whoa, wait, this is not practical for two reasons, right? One is measuring the full state at the output. If you want to seed a model, measuring the full state of the output is not tractable. The second is predicting forward in time is also intractable. These are both intractable things we know in the quantum regime, right? And so the point of this work is to kind of address those and have solutions to both. The solution to the first one is that instead of measuring the full state, you don't need to measure the full state in order to see the models that we're going to use. You just do something like classical shadows to measure the low weight powers. If you're not familiar with classical shadows, it's an efficient technique to measure a subset of observables in your system. And the point is we can do with just a subset of observables. And the second part, predicting in forward in time is intractable. The solution there is to develop reduced order models for short time propagation. You use the fact that you only need predictions for a short time horizon to develop reduced order models for the circuit dynamics. Okay.
Can you explain the second?
Yeah, I'm going to explain. I'm not going to explain classical shadows, but I'm happy to talk about that at the end. But it's in this. This was developed in this paper. It's a fairly popular technique now. But I'm going to explain the second part. Yeah. So the prediction part. So let's think about what you might want to do, right? So remember the cost function. I'm again using the QAOA cost function here, the Ising Hamiltonian. But in general, your cost functions are going to be sums of local operators, right? It's going to be a sum of local operators. So what you're interested in is what is the value of this sum of local operators after a short time horizon, right? Now, because your circuit is also local, there's something called the light cone argument that you can use, saying that a local operator here can only grow to a bounded weight operator after a few steps of the circuit. So what you do is you say, I need a prediction for this quantity. I'm going to reverse my circuit. I'm going to go backwards in time and come back to the measurements that I can do at this layer. So I'm going to propagate backwards in time for a finite time horizon. That's order 2 to the d complexity, where d is the number of layers I want to go back in. Right? I've taken away my qubit complexity and I've traded it for the time horizon complexity. So this means that I have a limit on how far I can predict. But that's okay, because model predictive control says I only need to predict into a finite time horizon. And I can do this efficient. So I can do that exactly in order 2 to the d complexity. But actually, recently there's been work to do it even more efficiently through approximate propagation. So you might not care about exactly predicting those quantities. And so you can do approximate propagation as well. Okay, so here's again how you do the short time predictions, right? So let's say I want a time horizon that's set by this length, right? I would take what cost function I want to predict at this value, I would propagate backwards in time, and then decide what measurements I need to do here in order to get an estimate of those values. So then I just do those measurements using classical shadow. Okay. Is that clear or anything?
I have a question about it. So you're basically so you have your model Hamiltonian and mixing Hamiltonian again. Is it the same concept at this point?
If you're doing optimization, yes, but this is not restricted to optimization. Yeah.
All right. So when you don't know the coefficients that you're setting for those like light gray boxes.
Yeah.
Can you still get the same operator set to measure?
So it'll be a parameterized model. It'll be parameterized by those coefficients, and that's what you optimize. So now I'm going to have an optimization step that says so the locality of the operators is fixed, right? It's just the parameters inside them.
Mm-hmm.
And so I'll get a parameterized prediction at this point, and then I optimize over that parameterized prediction. So now there is an optimization step in this because I have a model I need to optimize.
So basically what I was asking, like, I mean, the number of Pauli strings that you need to measure, for example, there.
Oh yeah, that doesn't change with the
That
parameters.
doesn't change with the parameters.
Yeah,
Okay.
that doesn't change because that's set by the locality of the data.
Mm-hmm. Locality and like commutation relations with those operators that you use in these light gray boxes.
Yeah, that's right. Yeah, is there any?
Didn't quite follow what the goal with that backward light cone prediction was. Are you trying to reduce the number of qubits that you have to measure? Or
You're trying to do two things. One is you're trying to reduce the complexity of the reduced order model. and two, you're trying to measure just exactly what you need to measure at this point. Instead of doing full state tomography, because the observables you care about here will only be influenced by some subset of the 4 to the n observables that you have here, and you only want to measure those.
Still measuring all the qubits, but you're reducing the number of rotations.
You might need to still measure all the qubits, but for example, like this argument, right? So if your observable that you care about here is 2-body here, by the time it propagates past 3 layers, it only is touched by these 6 qubits. You only need to measure observables on these 6 qubits.
You have other observables.
Mhm.
Then you need to
Yeah.
measure the other.
Right. But
You've shown that it's better than doing a full state.
that's right. And importantly, the weight of the observables that you'll have to measure is always bounded by how far you go, right? And classical shadows, we know that if you have a bounded weight, you can always get a logarithmic kind of complexity of the measurement.
Maybe we continue.
Yes, okay, yeah, we're running out of time, yeah. Okay, so, yeah, this is, I already said this. So let me show you some preliminary results with this. So I'm gonna show you again plots of optimization, max cut. This is now a much smaller problem, 4 qubits. And the yellow line or the orange line is the Falcon result, right? These should be compared to the plots I had before. And the blue line is what you do with this PVQA or predictive model. And so you see that you can reduce the layers by like orders of magnitude, the number of layers you need. So you can converge in roughly, I don't know, 20, 30 layers here, as opposed to 400.
I see a tiny bit of a problem on the left one. You get stuck in the local minimum, I think, but
Yeah, here we've converged to local minimum. Yeah, so you don't get global minimum out of any of these. There's no guarantee that you get to global minimum. I should say, an important note here is we're not using the reduced order model here because the main thing we wanted to confirm here is that introducing a finite time horizon prediction can reduce the convergence time. But we're plugging in the reduced order model in the next step. So this is my last slide. So summary, this is a new adaptive variational algorithm. Importantly, in contrast to Falcon, it's adaptive and predictive, right? You use qubit measurements to predict for a finite time horizon to the future, and we show that improves convergence dramatically. Now, the classical computer has to do more, which is maybe more interesting for the HPC folks. You have to, well, actually, let me say, there's some optimization now required, right? Because you have a model that you need to optimize over the variational parameters in that finite time horizon. But the nice property about it is that it's noise-free. It's not influenced by shot noise and hardware noise, right? You have a classical model that you're integrating. And the classical computer's workload is more significant than for Falcon. You have to integrate and propagate the reduced order model. You have to optimize the parameters in the model. And at some scale, HPC will probably be required for this application. Okay. So let me stop there and acknowledge funding sources and projects that work. Thank you.